Hello, this is the screencast for Network Embedded Systems. In this showcase, we're gonna speak first about the introduction, who we are, what is our project name. Then we're gonna speak about the background so you can appreciate our project and understand what it's all about. Of course, then we will speak a little bit more about the specific application we have chosen, which is platooning. Then we will analyze a bit our implementation and the simulator we're using for this scenario. And then we're gonna showcase our simulator in action. You're gonna see how it operates, and we will close with our result analysis. So, our project title is Vehicle-to-Vehicle Communication Networks. You can see here our team members. Of course, this is a project done for the course Network Embedded Systems, as is taught by Professor Majid Nabi. So, the connected car. It is evident that every year that passes, we notice that the new vehicles that come into the market are more and more intelligent. They have more features, more connectivity, and can do more things than they could ever do before. To this direction, companies, industries, and even independent researchers are looking at vehicle-to-vehicle and vehicle-to-everything technologies as a potential solution. As an example of this, you can see that recently the company Volkswagen launched the new Golf, which is vehicle-to-everything enabled, provided of course by a chip made by Dutch company NXP. So this technology is also thought of being an important milestone for the autonomous car of the future. Keeping these things in mind, we can also see that there is a big EU project currently running. This project is mandated by the European Telecommunication Standards Institute, and it includes all types of communications inside vehicles, vehicle-to-vehicles and vehicle-to-infrastructures. Topics that this framework deals with are the automotive ITS security, automotive radar, and electronic fee collections, and more importantly to our case, efficient transport systems and road safety. So, there is a huge initiative for a common standard. All major stakeholders push for this. You can see here some, like Siemens and NXP, some company representatives, and of course the European institutes, who are pushing for the adoption of a common standard. This standard in particular is called IEEE.11p, also known as Wi-Fi P. So, what is Wi-Fi P? It is basically an amendment to normal Wi-Fi, IEEE.11, and it's made in order to address wireless access in vehicular environments. The frequency in which it is operating is 5.9 GHz. You can also see the frequency band here, and this frequency was allocated on August 2008 by the European Commission. There are 710 MHz channels operating on this, it's also worth noting. The standard is also designed for fast transfer of data. This is done because in a real application where cars are moving, we cannot guarantee that the link will be long-lived, so we don't know if there will be enough time. It is crucial that everything that packets need to be inside is already delivered in the short time they're going to be there. So, in comparison to normal Wi-Fi, there is no association and no authentication of the messages. Additionally, Wi-Fi P has some advertised metrics. It claims that it has 1 kilometer effective range, it can handle maximum 108 km per hour relative speeds for its cars, and it boasts a maximum 27 megabits per second bit rates. The medium access is also CCMA based. Now for a specific application, the vehicle-to-vehicle application, this is called platooning. As you can see in the pictures, it is an unnamed car which is driven with unnamed cars which are following a platoon leader. The platoon leader is a human, and the named cars of course have no drivers. So, the benefits of such a technology is that it's a more efficient use of the highway. That makes traffic jams less common and less severe. Also, it's far safer because we eliminate the human factor who can make the mistakes. Additionally, by the reduction in air drag, we can observe fuel savings. This of course means less CO2 emissions and saving costs for the companies. In this simulation scenario, we're mainly simulating a platoon of trucks. And while we were thinking about this, we thought that these questions are the more important ones. We first wanted to see if such a simulation resulted in a safe platooning application, if this technology, platooning, is or at least can be safe. Additionally, we want to check if with interference issues, if they exist in the links that the Wi-Fi P platooning is going to be using, and if the interference causes severe issues. Also, another thing we wanted to study is if the system can scale well. Maybe it can work for 3 or 4 tracks in a platoon, but can it work for 20? Or can it work with other cars that are Wi-Fi P enabled and do not take place in the platoon? Also, it is important to also notice if the protocol can support the industry's needs. So there are many factors to take into account, as you can probably imagine. One of these questions was what simulator software we will use, and this was a question that actually we spent a lot of time thinking on. How realistic will be the simulation? Will we simulate every detail of the track? Also, another important thing is how we're going to simulate the link quality, and what do we mean by interference. A big question that came up with also is the network topology. What sort of network we're going to be using? In the end, we opted for the standard Wi-Fi P topology, as we will see in next slides. Also, the question came how to simulate normal and realistic track movement. So, in order to answer these questions first, we have to see the implementation we used. And by implementation, we first need to see the actual simulators we used. Our basis is Omnet++, which is a simulation framework. On top of Omnet++, there is Vanes. Vanes is actually the actual simulator that is handled by Omnet++. And Sumo is our realistic traffic simulator. So what is going on is that Sumo can have access to Vanes and Vanes to Sumo in order to get the data, and then Vanes simulates the vehicle-to-everything communications. This combination is established already in the vehicle-to-everything sector, and we thought that would be nice to have an extra confirmation for our job. However, as we experienced, this is badly documented, and we had lots of problems with this. Thankfully, after more studying and research, we found Plexe. Plexe is actually an extension to Vanes that is made with platooning applications in mind. The good thing about Plexe is that it eliminates the complexity. The way it does this is it gives us a single point of controlling the simulation, so we don't have to deal with 3 or even 4 applications, but just one window. Additionally, it's far better documented, so we can search on how to do the things we want to do. And we should also mention that this was actually a project done in 2016 by Dr. Michel Segata from University of Trento. Here you can see Plexe's logo and some pictures of our application. You will see more in the video later. So, what were the design choices and the assumptions that we made along this journey? We first decided that we're going to be simulating Wi-Fi P communication. Also, judging by the literature we had studied, we noticed that there are already applications with less than 4 or 5 tracks, and we thought that it would be better to investigate scenarios with more tracks. Our limit was 20. We're also considering average track speeds ranging from 35 km per hour to 80 km per hour. Our main focus is the network latency and the distance between the tracks. This is the parameters that we're looking out for. The simulation scenario is also already defined, platoon of tracks, so they're already working. We don't simulate the joining mechanism. Then, in our simulation, the leader initiates an emergency stop, 5 seconds in the presentation. The controller also plays a very important role. We actually use the standard one provided by Plexe. we tested the same scenario with tweaks in various network parameters. Such parameters is the packet size and the drop rate. So, without further ado, this is our simulation in action. Here you can see the commands used to run the simulation. These red cars represent our tracks. In this example, they gradually accelerate and then decelerate, so it's a normal application. You can see that the gap they leave between them is relatively huge, but the movement is smooth, so there is no danger of collisions. The simulation should stop at the 30-second mark. It stopped normally as expected, so this is our second simulation. In this one, we show a braking application. So, we start like the previous time, but now, at the 5-second mark, an emergency stop has to happen. The leader initiates this, and the other cars follow. You see that they stop pretty close, but then again, it was nothing dangerous. No collisions. Everything went smoothly. All the cars are gradually stopping. You can see by the stopping lights that they're braking. And again, we have a smooth scenario. No unfortunate incidents. So let's now speak about our results and our analysis on these results. It turns out that most parameters we were tweaking in our simulation, such as the packet size, the number of tracks in the platoon and the leader speed, had little to no impact on the actual metrics. These metrics are the inter-vehicle distance and the latency. The average or mean values of these metrics was observed to be 10 meters for the case of the vehicle distance and 0.13 milliseconds for the case of the latency. However, when we added other Wi-Fi P enabled traffic in the scenario, we observed a similar mean value, but the distribution was different. This time we had more peaks. Of course, this is to be expected because these cars that we added are in different places all the time. So if a car happens to be close to one another and happens to send things and packets, then it might be that we have some kind of collisions in the packets. Additionally, what we also observed is that the packet loss radio had considerable impact. In the low packet drop scenario, where we had a 10% packet drop rate, the latency was actually slightly improved. The latency we observed was 0.11 milliseconds. However, in the loss scenario, where half of the packets dropped, we see a dramatic increase. The latency was 0.25 milliseconds, which is very significant and above what these sort of applications can handle. For reference, we can say here that in the literature we found that a value of 0.15 milliseconds is the maximum value that these applications can handle. So, as we continue to analyze these results, we can see that even in the worst case scenario that we did, where we simulated a lossy communication system, lots of interference from other Wi-Fi P enabled cars, big packets, 20 tracks in the platoon, and the maximum speed, 80 km per hour, we did not observe a crash. However, it's also worth noting that in some simulations we tried to use our own controller instead of the default one. This time the tracks crashed, even in the standard scenario. That shows that the communication part is not the only important aspect of vehicle-to-everything communications. This should be taken into account when evaluating network dedicated to vehicle-to-everything communications. So that allows something to be said about the feasibility and future improvements on this work. Of course, provided with a good controller, we think that a large-scale deployment of platooning is possible. However, the distance between the tracks is relatively relaxed. Currently we observe a 10 meters gap. This, however, can be improved again by a good controller. Additionally, a potential problem that could be observed is the link quality. Our literature seems to suggest a 10% packet drop rate is reasonable. However, field tests should be conducted in order to verify this and other parameters. It is very important to have actual field experience before implementing a worldwide solution. Also, it's worth noting that information security and integrity should also be taken into account. The limits of our current technology should be clear, and any driver or passenger in the car or truck should know how secure this solution is. So, this was our showcase. Thank you very much for your attention. I hope you liked it.